Hi there, everyone. So this week we're going to do lab 4, the projectile. So you log on to Canvas, go to our course folder, click on modules, and then click on this this lab menu, the projectile. So once you click on that, this is what you're going to see. So let me bring up the lab. All right. So what is the projectile? Projectile basically is something that you launch and it's going to travel and it's two-dimensional. So it's something like this. So this is basically the, how you construct it. So you have a mini launcher and you have the steel ball that is docked in the launcher, and you're going to change the angle. And then at each angle, you're going to launch you're going to fire the steel ball, and it's going to it's going to travel like projectile, and it's going to land on the tabletop. And on the tabletop, there's a sensor that's connected to a computer. So so it's going to, the computer is going to measure the flight time. In addition to that, it also provides information that you can estimate the initial velocity of the ball. So you've done enough physics problem to know that when you have, when you have a projectile located, so let's say this is a coordinate, and the coordinate is set, you can see the dashed line here, and let me just, you see the dashed line here. So this is basically your initial height. So we call that y naught, and then this, this is the location. This is the location of the projectile. This is the origin. So it traces out its trajectory like this. Okay. So and this is the origin. So this is initial height y naught, and then this is the total. This is the horizontal displacement. Okay. All right. So, and you can see that, from this origin to the base, this basically this distance does not change, which we assign the letter L to indicate, because it does not change. So in the lab, when you find a projectile, when travel through air and landed on the sensor, it's going to leave a mark on the sensor. And then you would use a ruler to measure from the base, from the end of the base to where the touchdown is. And this, we call that X prime, not X, let me see. We call that X prime. Yeah. Okay, so you're going to launch the projectile 5 times at each angle, and then you're going to have, so for that 5 data points for each angle, you're going to take the average. So this X prime, the final result of this X prime is the average of the 5 data points, and then the X prime here. This is your X prime. Of course, you know that it's not your horizontal displacement, because your horizontal displacement should also include this L. So this L will be given to you. And so your the experimental value of the horizontal displacement of the projectile is then xm is equal to L plus X prime. Just based on this diagram, we know that the L does not change, and your X prime is the average value of the 5 data points. And so for each angle, you're going to have the experimental value of the horizontal displacement, and you're going to change the angle from 5 degrees all the way to 85 degrees at let me see at what degrees increment. We're going to go over that, but it's some increment, and then so you're going to have a collection of data points for each for this projectile motion, and then with the time information, we're going to use the equations of motion, which is this equation. This equation tells you that, the horizontal displacement, which is vertical displacement, which is y minus y naught, is equal to initial velocity times sine of theta, and then times the time minus 1/2 gt squared. So we arrange this, then you'll be able to figure out what is the the vertical acceleration, which is free fall acceleration. So when you do the plot, you're going to get the slope, and you're going to compare the slope to 9.8 in order to get the percent error. Okay, so let's go. So that's basically what you're going to do. You know, just to find the accelerations of the projectile in the vertical direction. And so, and this is the diagram that basically tells you how to figure out the, you know, the horizontal displacement. And so the construct will be that the ball is going to pass in two folder gates. It's not shown here, but the ball is going to pass two folder gates, and that two folder gates has a distance, or the separation between the two folder gates is the distance that the ball travels. And then the computer is going to measure time. So based on that, you can kind of estimate the initial velocity of the projectile. With the information of initial velocity, which is v naught, then you'll be able to calculate the theoretical value of the horizontal displacement. Because if you remember, let's say you estimate the initial velocity v naught, then the horizontal displacement theoretically can be calculated using the initial velocity and then times the cosine theta, which is the so this term v naught times cosine of theta, that is your initial velocity in the horizontal direction, and then this whole thing is going to time you know, multiply by t sub l, and t sub l here is the total flight time. So this will give you the information of the theoretical value of the horizontal displacement, which you're going to compare to the experimental value of the horizontal displacement, which I wrote that earlier, which is xm. Okay, and your xm is basically equal to L and then plus x prime, using the average value of x prime. Okay. All right, so that takes care of the horizontal, you know, component. And then there's a vertical. So vertical, let me scroll down. Before we talk about the vertical, let me just say that this launcher comes with 3 different ranges. So we're using the smallest range, and we launch it, and then we launch it, and then we change angle, and then launch it again, and then each time, you know, each time is going to, you know, you're going to do it 5 times. So when you go down to analysis, before we go to an analysis, let's look at the table. So the table here, you can see that it is structured as you have 5 degrees, and then 15 degrees and 25 degrees. In other words, you're going to have data from 5 degrees all the way to 85 degrees in a 10-degree increment. And at each degree, when you launch the projectile, the system is going to measure the initial T naught, which is used to estimate the initial velocity, and T sub L, which is the total flight time, and x prime is the distance measuring from the base of the base from the touchdown. Okay, and at each angle, you're going to you know, you're going to fire the projectile 5 times. So so you have the data points, and then you need to figure out the average value. Okay. And so when you have the average value, you use the average value to find, you know, to find the subsequent value on the second page. Okay, so all this page will give you the informations of the T naught, TL, and X prime of the average value at each angle. And then on the second page, the D is the separation of the folder gates, which is used to estimate the initial velocity. This will be given, and L is also given, which is the origin to the edge of the base, and Y naught, which is you know, where the projectile is located in reference to the origin. That's also that will also be given. And then you have the and then based on that, you can estimate the initial velocity for all the angles. And then you have the horizontal distance, and then you have the vertical distance. Okay, which you know, XM and we went over how to calculate XM. We went over how to calculate XT. And then what about the plot? How do we do the plot? So that's come back to the analysis. So when you read through the analysis, of course, this other thing, this equation tells you how to calculate your XM. We went over that. And this equation that tells you how to calculate initial velocity. And then the D here, remember everything has to be in SI units. If you're given distance in centimeters, you need to convert it to meters, okay? So this is how this equation tells you how to calculate V naught. This equation tells you how to calculate L plus X prime. X prime, of course, remember, that's the average value, okay? And then how to calculate theoretical value of the horizontal displacement, which is this. V naught, which is from this. So V naught, and then cosine theta. Theta, of course, is is a variable that change from 5, 15, 25 degrees, and so forth. And then TL is from is from the computer. So you can calculate your XT and XM, and you can compare these two values. So this two value, you treat you put the theoretical value in the denominator to calculate percent error. Now, regarding vertical, this is the question. Remember, you're using the equation 1, which is the vertical displacement is equal to the vertical velocity, initial vertical velocity times time minus 1/2 gt squared. So when you rearrange this, you will have something like this. Okay, so you have, and this term is basically this term is the V naught sine theta, which is the vertical component of the initial velocity times TL, and then this is G times 1/2 t squared, and then minus Y naught. So you want to calculate. So you want to calculate in the Excel. You want to calculate V naught sine theta TL. You want to calculate this term. You want to calculate 1/2 TL squared. Why do we do that? Because when you have this and that, and then we're going to plot this quantity versus this quantity. So when you plot V naught sine theta times TL versus 1/2 t squared, then the slope, you're going to expect to get a straight line, okay? And that slope is the experimental value of the acceleration, okay? And whatever that value is, you're going to compare to 9.8, because theoretically, we'd expect it to be 9.8. So whatever slope that you got, that is your experimental value of the acceleration compared to that. And then in the your line fit equation will give you the vertical the y-intercept. That y-intercept is the value that you're going to compare to y naught. Okay. So when you do the comparison, you can just drop the negative sign and just compare whatever that you have, the y naught here and the y naught there. Now, the other thing I want to mention to you is that the y naught you're given is in centimeters. And when you do the line fit, when everything is already in SI unit, which will be in meters, so whatever intercept that you got is going to be in meters. So when you do the comparison, again, the value you're given should convert it to meters in order to be comparable to, in order to be compared to the y-intercept from your fit. Okay, so it's basically what you want to do for today's lab. So let me bring up the data. So you would, let's see, you would. So the recording again, will be uploaded to this, lab instruction, subfolder. So it will be available for the lab data. You want to click on the lab for projectile data. So download that data to your to a desktop, to your computer, and work from there. And then what I'm going to show you is the data. Let's say I already opened up the data, download to my computer. So these are the data. So you can see that the data that you have here is that at each angles, So all this data points out there. So you want to find the average value. And so this, I think you should just key into the Excel and then do the average. It's very easy. So because once you key into that and then just move it across, if you remember, move your mouse. If you've done the average for the first one, just move your mouse and then until you see a solid cross and drag it across, and it's going to calculate the average for the for all the quantity all the quantities along the same row. Okay, so I think it's best that you key in the data to the Excel. Don't just key in the data to your calculator, because if you mistype a data point or two, you're going to get numbers wrong, and then it's going to affect it's going to propagate the error is going to propagate to other subsequent calculations. So these are the data points. You can see that the data entry might take some time, so it's you should start working on this lab as soon as possible. And once you have the data points, the average, it is the average value that goes into be used on the second page. And as I mentioned, the D here is given, so it's 10 centimeters. And the L is also given, which is 13.35 centimeters. And Y naught is also given, which is 4 centimeters. So from the equation in the analysis, which we just went over, you can calculate your initial velocity, and you can calculate your XM, you can calculate the XT, and then you do the comparison, okay? And then let's see, and then if you look at the vertical, the vertical distance, this for this table, the slope is from the graph. You want to calculate V naught sine of theta times TL, and then you're going to create another column, 1/2 TL squared, in order to do the plot, and the slope is going to give you a value. You're going to compare 9.8 in order to calculate percent error, and do the same thing for the Y. Okay, and the other thing I want to mention is that you have the T naught and then TL. As I mentioned, T naught is the one that goes into that you use to calculate to find the initial velocity. TL here indicate the total flight time of the projectile. Now, when you use the Excel to do the calculation, I just want to show you because Excel does not take Excel does not recognize degrees. So when you want to do, let's say when you want to do cosine 5 degrees, how do you do that? Let's say cosine 5 degrees. I mean, if you just punch into a calculator, then of course that's easy, right? But then because you're going to do a lot of calculation, I do not recommend you to do that. You would so in Excel, click on the empty cell, hit equals, and then type in COS, okay, and then parentheses, and then you would have, let's say, the 5 degrees over 108, so it converted to radians, and then multiply, so the star, and then times pi, just write down pi, and then a pair of parentheses with nothing inside, and then close the parentheses. So in other words, this is how you calculate cosine 5 degrees in Excel. You would do this. On the empty cell, hit equals, type COS, and then parentheses, and then you have the 5, you have the 180 degrees times pi, and then parentheses. Okay, if you want to do sine, you just change the COS to SIN. If you want to, so let's say, if this is not just 5, let's say this is the your 5, you organize your data point, that is, let's say this is your angle, so you have the 5, you have the 15 degrees, you have the 25 degrees, and so forth. So each one is on the Excel, it has its own cell number, right? So when you do the so on this empty cell, you would just say that's equals COS, and then parentheses, and then click on the cell, So let's say this is A7, then just click on the cell and then type in whatever. And then once you do the calculation, and then you have the value, and then move your mouse until it becomes solid cross, and you just drag it down. Then it's just going to do the calculation for you. So that's why, you want to key in the data to the Excel. Do not try to key in the data to the calculator, because you're going to repeat the calculation for a lot of times when it's just basically the same calculation. When you do Excel, when you click on the cell number, then you get that number. And when you drag it down, that cell number is going to change automatically. So you don't have to key in every time. You just key in one and then just drag it down, and then you do that, okay? So that's same thing for, a lot of calculations here. If you're not familiar with, I strongly encourage you, to work with your group members, work together on doing the data analysis. And if you really have a question, I'll be in the Zoom, come to my office hour, or we have TAs, they are in the Zoom room, you use the same Zoom link. They can help you to do this, okay? If you don't have a question, then this is the data analysis is pretty long, so I want you to get a head start. Do that as soon as possible. Don't wait until the last minute. Okay.